No mä soitan, jos tulee joku pahekki.
Okay. Then this. Okay, so now we're finally ready, good to go. How is, by the way, is there echo to this one? A little bit, I guess, but not too much. Okay, so anyways, so today is a special day for two different reasons. The first reason is obvious, and that's because we have a visiting lecture, and the visiting lecture will be delivered by Dr. Heikki Niskanen.
Heidi
Niskanen. Now, Heidi is from EDR Medisort, which is, your office is located in Tampere.
Yes, in Finland.
Yes, and now the second reason why this is a special day. The second reason is the fact that right after the lecture, you have an opportunity to see your exams. This is an opportunity, you may take it or you may not take it. So if you want to see me right after the lecture, I'm available in my office. So we can take a look at your exam paper together. This is an opportunity here to make it, start to build the case and try to raise your grading from the midterm exam. So you're not happy? Or you're happy? Not happy, so you come to see me. And remember, if you take your mom with you, it's going to help your case. Are you going to take your mom?
I can't. How about if I take him?
No, that's not all right. So it needs to be a relative that you're taking with you.
How about my girlfriend?
No, that's not good. So it has to be.
Well, my parents don't live in here, so.
Okay. Anyway, so right after the exam, I will be here when we're closing the things. I will take my computer and everything. So then we will walk together to my office. Okay? So how many of you would like to see your exam paper? 3, just 3.
Others more?
Others are happy. You are happy with your exam. Okay. Now, without further ado, Heidi.
Okay, thanks.
And I will text how the streaming goes on. And if any problems, I will come back.
Okay, very good. Thanks. Can you hear me all right? Very good. So I'm Heidi Niskanen, coming from EDR Medisort, and we are basically we are a company that is building digital twin solutions to our customers. And first, I'm gonna just briefly go through what our company does, and then talk about a bit of sort of current global trends, because environmental and sustainability issues are very important to myself, so I want to address them also, and then use them as a nice excuse to do some simulations. How many of you are familiar with physics-based 3D simulations? Yeah, okay. What have you been doing? CFD, FAA, or? Finite elements. Okay, right. So I'm not going to talk about anything in great detail. I'm just going to give a very general overview of how those different bits and pieces can be connected together to finally build up digital twins, which can help then in various things, for example, for our customers. So I hope you can hear this video, so let's try. This is a short video showing what our company is doing. It's in Finnish, but there is some English subtitles, so I hope it can deliver something to everyone.
Nykyään meidän asiakkaat odottaa, että ne tuotteet toimii heti siitä ekasta versiosta lähtien. Ne odottaa, että ne toimii keskenään, juttelee keskenään, kykenee muodostamaan kokonaisvaltaisia ratkaisuja. Tällaista tekeminen on tosi vaikeaa, eikä oikeastaan voi mennä markkinoille keskeneräisellä tuotteella. Tässä kohtaa ainoa tapa tehdä nämä on tehdä se digitaalisesti ja varmentaa, että kaikki toimii. Mä vastaan Suomen ja Ruotsin digitaalisten kaksoisten tuotekehityksestä. Vedän meidän projekteja muun muassa Rolls-Roycella, missä tehdään heidän potkurivaihteestaan täysin digitaalinen versio. Digitaalinen kaksonen on meille sellainen palvelu, jossa me tehdään asiakkaan tuotteessa digitaalinen versio, laitetaan se pilveen pyörimään siten, että kun sitä oikealta laitetta ajetaan ja käytetään, niin samaan aikaan siellä pilvessä se digitaalinen kaksinen kertoo, vaurioituuko se laite siitä, kuinka pitkään se kestää vielä, tarviiko sille tehdä huoltoa. Potkuri osuu vaikka jäähän, niin se näkyy suoraan, mitä se vaikuttaa.
Me oikeastaan tarjotaan kaikille teknologia-alueille jotain. Meiltä löytyy mekaniikkaa, sähköä, virtausta, lämpöä, visuaalista suunnittelutyökalua. Meiltä löytyy oikeastaan nykyisestä portfoliosta melkein mille tahansa asiakkaalle. Hyvä esimerkki digitaalisen prototyypin edusta on se, että jos joudutaan tekemään vaikka esimerkiksi antennin muovisuojakuori fyysisenä prototyyppinä, niin sen muotin tekeminen tai tehdä siitä 3D-tulostuksella fyysinen muoti, niin siinä saattaa mennä päiviä, viikkoja, ja se kulu, mikä sitä saattaa aiheuttaa, se voi olla tuhansissa tai jopa 10 000 eurossa per yksi ainut prototyyppimalli. Ja digitaalisella mallilla me saadaan kokeiltua se malli ja varmistettua, että se toimii. Se ensimmäinen prototyyppi on todennäköisesti hyvin lähellä toimivaa valmista tuotetta.
Tällä hetkellä simuloinnissa multifysiikka alkaa näkymään. Kun huomataan, että pelkkä virtaus- tai mekaniikkalaskenta ei riitäkään siihen, mitä sä ajattelit simuloida, niin näitä joudutaan yhdistämään. Ja aiemmin tällaista yhdistystä ei välttämättä pystytty toteuttamaan. Se saattaa olla johtunut esimerkiksi laskennallista haasteista, että ei saada tarpeeksi kovaa rautaa laskemaan tätä, tai ei vaan pystytä yhdistämään mekaniikkaa ja fluideja toisiinsa. Ja viime vuosina tähän on vihdoinkin päästy kunnolla kiinni. Ja tämä alkaa selkeästi näkymään kaikilla aloilla yhä enemmän ja enemmän. Esimerkiksi sähkömagnetiikkapuolella, joka on aiemmin ollut melkein täysin pois kokonaan. Tällaisen yhdistäminen moottoreissa, kaikissa elektronisissa laitteissa tulee näkymään. Itse ajava auto voisi olla tällaisesta aika hyvä esimerkki. Käytännössä auto, mitä se näkee, täytyy simuloida sähkömoottoreissa on magneettikenttä, joka vaikuttaa mekaaniselta puolelta. Tässä voi olla mukana tärinä ja värinä, joka sitten myöhemmin vaikuttaa elektronisiin komponentteihin, saattaa murtaa asioita. Ja nämä kaikki ovat yhteisvaikutuksissa toisiinsa. Jos yksi komponentti pettää esimerkiksi, silloin pettää kaikki muutkin.
Fyysinen laboratorio ei pysty enää ainoastaan yksin vastaamaan näihin kaikkiin haasteisiin, mitä tässä kentässä on. Jos halutaan tehdä ympäristöystävällisemmin ja nopeammin tuotekehitystä, niin digitaalinen laboratorio on aina vaihtoehto. Se ei tarkoita sitä, että fyysinen testaaminen loppuu kokonaan. Se tarkoittaa sitä, että ne havainnot, mitä sieltä fyysisessä laboratoriossa on löydetty, viedään digitaaliseen laboratorioon ja otetaan siitä digitaalisen laboratorion skaalaetu käyttöön. Eli esimerkiksi ajetaan 5000 digitaalista laboratorioa samaan aikaan pilvessä. Aina silloin tällöin me tehdään meidän asiakkaiden kanssa sopimuksia siitä, että me saadaan antaa pieni julkilausuma näistä meidän digitaalisista laboratorioista. Ja ne itse asiassa löytyy meidän nettisivuilta. Sieltä voi lähteä katsomaan, mitä me luomme tehdä meidän kanssa.
So, did you get an idea what we are doing, basically? Yeah. So then few words about the company itself. We are no purely Nordic company merely. We have 2 offices in Great Britain as well. And in Finland we are located in Tampere, and we have a couple of satellites in Jyväskylä and Kuopio. And in Sweden we have offices in Gothenburg and Västerås. And in Norway, Oslo, and then in Denmark we have Copenhagen office, and Sheffield and Edinburgh in Great Britain. Currently we have, I think we go closer to 130 people, so we are altogether in all of our offices more than 100 people, and in Finland also 25, I think so, and we are growing quite fast. And in Finland we basically have this digital lab based on Ansys solutions, but in Denmark and in Norway we have also this virtual fabrication issues, which is based in Tekla and that kind of building information intelligence technologies. And we, well, basically we have been also given some awards, or we have been noticed as being of one of the most innovative IoT companies. So we have been awarded already in quite a many places. So it seems to be globally also interesting what we are doing, and it can be also seen from research initiatives as well. We were called in one research consortia which was based in as one University of Africa. So this is quite unique what we are doing. So our talent is needed nearly globally nowadays. But in the Nordic region, we are kind of the technology leader in this digital lab concept we have established. And here are a bit of the people who are working with us. We have technicians obviously doing CFD, FVM, electromagnetic simulations. Then we have account manager, we have technical account managers, and other salespeople. So there is quite a variety of what type of people we need in our processes and in our business. So there are quite a lot of basically opportunities, but especially we are in Finland, at least we are desperately seeking some technical people. So if you're about to graduate shortly, so go and follow our websites to see the open positions. So then, any questions regarding our company? Okay. So then I'm just gonna go through a bit of what I think myself that is something that's quite urgent and something very current going on in the globe in general. So I think we can start with this video again to give it an introduction.
The world is changing. Industry requires more fuel-efficient vehicles. People are calling for cleaner air. Governments are mandating greener appliances. To meet these demands, engineers must find new ways to innovate. The old ways of bringing products to market are no longer sustainable. There is only one path forward: engineering simulation. The market demands change. The future demands a breakthrough. There is only one company with the depth and breadth of simulation experience to create these breakthroughs: ANSYS. A breakthrough designing fuel efficiency into all of our machines, into all that we do. A breakthrough in rethinking simple products that we take for granted. By innovating new ways to save water. A breakthrough in engineering new ways to climb higher. By creating ways to save energy. Innovating lighter materials. Optimizing the performance of advanced products. Breakthroughs that will revolutionize the way we live. The way forward. The way we experience the future. Using the power of simulation, engineers can turn this planet green. Engineers can dramatically reduce waste and inefficiencies. We can engineer a breakthrough. We can fly higher. We can change the world.
all about using less material, energy, resources, whatever you name it, air pollution less. The big cities are suffering from bad air quality, which kills tons of people as we speak. So basically what we are currently facing as a society are pretty much different things that considered maybe a few hundred years ago. So there are things like population growth, which comes with urbanization and transport, decrease of resources. We will eventually run up with oil, for example. We cannot use it eternally. There has to be some new ways to be developed to produce energy, use our existing resources more wisely. And of course, the big thing everybody's talking about is this emission growth and climate change, which might affect quite a lot on the life on this planet. So we are facing quite a big challenges, but also opportunity at this stage of our development. And that in general demands for quite a lot of new technologies which needs to be developed and innovated to be able to continue living in this planet, so to speak. And what it then means for engineering is, as we saw from the videos, that we want to use less prototypes, physical prototypes, which kind of unnecessarily use physical material. So we need to tackle these things, but maybe in a different manner that we used to. So basically, we need to ensure things like functionality, safety and resource intelligence from the very beginning of for example, product development cycle. So there is no necessarily time or resources to start doing it in the traditional way that you build up a prototype and then you test it a few times and realize that, well, this is not working, we need to come up with something else. And maybe you have spent already half a year or even more in doing so. So today it's kind of the thing that things go very fast. The business doesn't have time to start waiting for people to develop something in 5 years. It needs to be like in the next quarter. So demands for engineering from that perspective also is kind of different also from what it used to be. Less time, less material, and so forth. And currently there has been 11 trillion of global, 10% of global GDP potential recognized in these type of fields like IoT and industrial internet, big data and machine learning, additive manufacturing, autonomous robots and autonomous everything in general, mass customization, composite material, circular economy. So everything is kind of rolling around these things that the society is claiming when it comes to resource efficiency and that kind of things. So there are kind of a lot of fuss around these type of things. I am sure you have also heard about these in the news and everywhere, that these are kind of the things that will drive the business and drive the development further. So trying to sort of approach the simulation things gradually, starting from the big picture, and then basically trying to tackle the subject in quite a big perspective towards smaller and then bigger again. So first of all, why do we simulate or do experiment or build prototype as a first place? Because, well, things needs to be tested and they needs to be developed and approved. You cannot just put your autonomous car on the road without testing it properly, it might then end up killing many people if it's going totally recklessly around the roads. So we need to have some kind of a guarantee that things that we have been developing and building, that they do actually work. So that's why typically we use simulations or physical lab tests. And maybe that it's coming obvious from the motivation I tried to give just a few seconds ago, that preferably it's good to do these in a digital lab by simulations, not always building expensive and time-consuming physical prototypes. And also for this, there is a demand for optimization, and that is something that is much easier to be done in a digital lab concept or by using simulations instead of trying to build many versions of your product and then trying to test it and then trying to tune it from here and there. Instead, you need to consider the big picture from the very beginning. So that's why the simulations are coming into more importance and in the focus of everything. And well, basically, as was mentioned in this company introduction video, this is something for everybody. So every industry will benefit and is already benefiting from simulations. And it's estimated that every engineer by 2025 will utilize simulations. Not necessarily that you would do it by yourself, but at least someone from your team or someone, your colleague is doing them, and you may need to have some kind of an idea what it means and what kind of results you get from those. So, sorry, it's kind of all around, not just in nice talks. And why it might be good for you also to get involved with simulations. I got this last week from one ANSYS director working in the US. I'm not quite sure if this is a global or American thing, this table affecting, for example, on salaries. But here on the left side, there are some skills that most probably help you earn more. And there are, for example, ANSYS simulations, finite element engineering, and that kind of things that may boost your salary as well, and not so much as the things that have been popular recently, like MATLAB or that kind of things. So it's going more into these 3D simulation direction instead of these regular things that you might have been using or using still. And then something that I always want to kind of highlight is that you might think that it's very easy thing to do simulations. Obviously, it is very easy thing to get some nice pictures. So you can just click here and there with the software and push the start button to have the solver running. But then the results may still be total rubbish. So you really need to know what you're doing, and not only to do simulations, but especially if you are in a position that you need to actually solve some problem. There is some challenge, something is breaking down or failing. There is space rockets going out from the orbit, and you need to solve the situation. So you really need to know what you're doing, and you need to know the background, and you need to know what you are doing. You cannot just be clicking the simulation tool. So if there is something fatal going on, or not even extremely fatal, but something that is, for example, negatively affecting the business, some machine is not working in optimal way, optimal way, so it may consume too much, or it's somehow not working as it should. So then you kind of need to be on top of it all to understand that what's really going on, and what is this that caused this thing to begin with, and then obviously the big thing, how to fix it, and then in the longer run, if it's something really awful, then it doesn't have to happen again. So I kind of want to highlight the importance of understanding the big picture and the phenomena and everything that is taking place in, for example, in a product, to be able to utilize these technologies in very efficient way. And well, I don't know, I'm a physicist myself, so I love obviously theory and proving equations, and I have been doing it for like first 10 years of my studies. So I don't know, are you fans of doing pages and pages of theory and proving and calculations? No? Okay. Well, I still want to say that it's important to know the theory, so I guess you have those theoretical courses here as well, which not maybe your favorite things to do, but it's still important to know those things, because if you don't, then you cannot solve the problems you might be facing. So this is the kind of the key to understand these big things, to start from the maybe super boring things, but you need to have them in your back pocket to be able to save the planet, so to speak. And well, obviously we need those theories as well, because otherwise we wouldn't have any applications. If we wouldn't have Albert Einstein or Katherine Johnson from NASA and so forth, so we might be lacking quite many nice things we have right now. So I still would like to take the opportunity to encourage you to embrace the theory as well, so don't throw it away. So then kind of approaching this advance of simulation part, and please, whenever you have some questions, just interrupt and ask, so I don't need to just give this monologue by myself. And I have been suffering from pneumonia, so my voice is still quite low, so I'm trying to survive through this lecture, so I'm very happy if some of you will interrupt me as well. So then, going to this greatness of simulations, I'm going to show you one cool example, hopefully.
Volkswagen Motorsport is an ambassador for the Volkswagen brand. So the board asked us in 2016 to have a look on future technologies, and we identified Pikes Peak as the best platform for a manufacturer to show electric race car technology and also bring a big awareness to e-mobility.
The first design work was done in November, and the car was driving end of April. So we could not rely on testing, we could not do 2 loops of development, so simulation was the key.
When ANSYS approached us the first time, we straight away knew we had the right company talking to us, and what we liked was that ANSYS also saw this as a proper challenge to have this 9 months to be ready in America where the car that had to go up the hill and try to beat the electric record. So very quickly we were cooperating very close together.
Simulation and calculation of, let's say, aerodynamics or the structural components or the battery design plays a major role. And without this, you won't be able to build a competitive car. We spend a lot of energy with ANSYS to be able to simulate and define the best battery concept for the race.
The main objective was to beat the E-record, but for us also it was to show that Volkswagen is and wants to be the leader in e-mobility, and that we are ahead of what the technology is today.
So, as in the video as well, you saw that they had like, half a year to come up with a record-breaking car, and they did it only using simulations. So I think it's quite impressive. They didn't only break the electric car record, but the overall as well. So they were able to come up with a winner car in half a year just by utilizing simulations. And that is also a kind of one of the challenges simulations can be answering to. Since, today, what we also quite often hear from our customers that, they complain that, we can only test one prototype at the time. Well, obviously you can understand it, that it takes time to build one and then test one, and then you need to make changes and test it again. So there is no way of building like 50 different prototypes to test them simultaneously. And one thing that I have also encountered when I was a consultant, I used to do some CFD consultancy, and there were quite often situations that the customer called that, this thing is not working, fix it. So then they obviously needed to stop the process, stop the engine, stop everything while I was working to fix the problem. So it's no use to realize late in the project that, this cannot be built. There have been situations where there have been some applications built, for example, in such a way that the piping didn't fit into the room reserved to it. So if those things would have been tested by using simulations, they would have been solved in the very beginning. And one thing also is this, that physical tests, they are expensive. And then we also hear these success stories that, we saved millions thanks to simulations. Or that our CEO wants to reduce time to market, which is quite common nowadays. The competition is very hard. There are people coming with the products all over, or the companies coming up with the products all over the globe. So there is time to market is faster. And then also this blending of industries, the things that is going on currently, and IoT and this resource efficiency and everything that is going on globally has kind of changed the need for new technology and new expertise. So these are one of the examples to which you can tackle with the simulations. And when it comes to product-specific challenges, is the thing that, obviously products are becoming more complex. You have a smartphone now, and before you had this very nice telephone where you just roll out the numbers and pick up the call, and there wasn't not too many bits and pieces wandering around in that device, no antennas or anything. So that's kind of the demand for today. Also, the thing that the products are operating in very complex and varying environments. For example, if you build a pump and then you put one into a Sahara Desert and the other one to Antarctica, obviously the situation there to operate for the pump is completely different. So those kind of things you can already take into account if you use simulations, and you can simulate the conditions where your product is expected to operate. And it's also something that it's becoming more and more difficult to differentiate yourself and your product. And obviously the lack of tolerance for design law flaws is something that no one wants to encounter. If you build something that is not working, then your competitor might have done it already, and then you're out of business. So demands are quite high today. and kind of highlighting the advantage of information in general, that while you are doing some product development and building your products and designing new things, it's nearly 80% of the costs that actually comes in a very early phase of your design process. So if you put some effort into that, you can actually save quite a lot of money and time and resources in general. And if you do simulations in very early stage, then you obviously can make better decisions because you have more information. You see things which are happening inside the product which you couldn't see otherwise. You can reduce costly prototypes quite heavily, and also avoid these unworkable designs from the very beginning. You don't need to build anything unnecessarily. So from the very beginning, you know that you're on the right track in building your thing. Oh, there was some nice animation as well. Yeah, as referred there in this one slide, showing some skills which might bring you some more salary. How many of you, for example, when you're doing your things, or do you need to do some engineering projects or that kind of things, do you use Excel or MATLAB, or what's your main tool to do this? For what type of applications? Gentleman in the back row, could you give an example how you have been utilizing those tools?
Well, I've been using Excel and
yeah, okay, right. So it might be very practical in some of the cases, but as mentioned, that things are getting more and more complex all the time. So you may not be able to tackle those things with nice Excel sheet, for example, but you need to use these physics-based simulations to be able to check out the different phenomena that is going on in your product. Maybe you need to do some overall designing to consider, for example, in a motor there are mechanical things, there are heat-related things, there are electromagnetic-related things, and those all need to be kind of checked together and validated to be working properly together. Because if there is some mechanical wear, then it affects into something, and if there is too much heat, then there might be too much overheating, and then the product as a whole may not work so properly. So these complex things, they usually require quite a lot of heavy simulations also. And yes, I hope that I am able to highlight and confirm you that simulations are actually cool things. But it is a sort of proven way to win. We see it every day with our customers that you save most and get the best products when you start using simulations in the very beginning of your product development cycle. The benefits are obvious, but I will still try to highlight these so that you remember. It's faster and cheaper, and then when you can check all those details from the very beginning, then obviously it will lead to better products, and that's also a way to improve your innovation. You can test things that you couldn't test with, for example, in a physical lab. You cannot change your physical prototype in the most wildest ideas you might get in the deep hours of the dark night in your head to come up with some cool solutions. So with simulation you can test those all, and you can do it just like immediately. So any questions at this stage? Am I convincing you? Yes. So you all love simulation after this one? And you will learn them more and maybe eventually come to work for us? Yeah? Well, that would be the ultimate highlight. So anyways, moving on with, moving into this digital twin part, which kind of then compiles all those bits and pieces together. And I'm gonna show some video again so my voice can rest a bit.
For decades, companies have used simulation as a product development tool to discover failures and flaws in their designs. Now, engineers are using simulation after their products are built, sold, and deployed in the field. It's called a digital twin, a complete digital replica that operates in real time, giving engineers unprecedented visibility into the performance of their products. Here's a simple example. This industrial pump has multiple sensors, providing real-time information. In this example, the sensor's data is fed into the IoT platform, where engineers can monitor the normal operations of the pump. Here, an anomaly is introduced, as a valve is closed, prompting an alert and the need to troubleshoot the problem. The ANSYS simulation platform allows engineers to evaluate all possible inputs and operating conditions. Users can model a complete system and integrate live sensor data, creating a near real-time environment. By reproducing the problem virtually with the digital twin, you can identify and analyze the cause, purpose, and test corrective actions. When an anomaly is detected, ANSYS takes data from the system model and sends it to the edge, on-prem data center, or cloud, allowing for automatic 3D simulation to model the specific nature of the problem. The digital twin allows for diagnosis and in-depth root cause analysis for physical assets in the field. Here, the root cause of the anomaly is identified by 3D simulation to be cavitation in the pump, as visualized by the purple vapor bubbles. The user can perform what-if scenarios on the digital twin for both testing and further optimization. With the ANSYS platform, customized user experiences can be easily implemented. This allows for ease of use and communication through similar graphical interfaces that are customizable for each user. At this point, the user validates the corrective action found on the system model, will remedy the problem on the physical asset through in-depth 3D on-demand simulation. Here, you can see that no more bubbles are present and the pump is once again operating properly. The cavitation issues have been corrected in the digital twin and can now be applied to its real-world counterpart. Digital twins require a complex and comprehensive knowledge of systems engineering. Only ANSYS has the breadth and depth of simulation experience to bring the full power of digital twins to your engineering challenges.
So that is actually pretty similar to what we have been doing to one of our customers. I'm not sure if I can say the company name aloud, but we have a corresponding case what we have doing for one of our major customer in the pumping industry, and they are now providing their pumps with a service with this digital twin and predictive maintenance options to their product. So. With this picture, I will just try to compile and demonstrate the different parts that you need to sort of combine together in order to be able to come up with the digital replica of your product. Maybe you already have spotted some things from the previous slides that you might be able to indicate what we maybe need to investigate in the case when we start developing a digital twin. Any idea? No? Fluids, for example, CFD. We need to check out how fluid or heat transfer phenomena are doing in our product structures. Some of you were familiar with FAM, So this is obviously one big thing that one needs to consider if the structure is durable enough, if there is enough amount of material, or is it optimized well enough for its purpose. Electronics. Nowadays, I don't know if there is anything being built that doesn't include some electromagnetic components. So that is obviously something important to consider. Semiconductors, those are getting more and more common in products. Optics. For example, I think I have one video showing about, for example, how to test drive a autonomous car, and there these optical things are quite important with respect to sensors and lidars and that kind of things. Software. You usually have software in the loop, something that controls your device, for example, some autonomous things. It usually have some control logic or something to tell the product that it's doing well or it's performing within the limits. And then obviously finally full system thing that can compile these all. So trying to get there towards digital twin or digital replica of your physical products. It obviously consists of a single component that most often they need to be checked separately, but if you want to build up a replica of your product, you need to compile all these things together. So what you usually start with it's to start up with one component at a time, and then basically you have those models for this single component where what you can use to start building up this digital twin. So basically this has been quite long the traditional way of doing things, that you perform, let's say, only CFD or only FAM or only electronics. But going towards this bigger representation of your product, you need to compile these all together so that it actually forms up this full system, full operational unit, so that you can show and study how your components are actually working together in the full product that you are designing or doing. So that is kind of the spot where these digital twins come to play. So well, maybe you already have quite a good idea what is a digital twin based off those couple of videos I showed you, but basically I'll just repeat it. So it's kind of an thing living its own life. It can be living in a cloud, for example. It is built from those single models by some tricks and magic. I'm gonna just go them through briefly also later, but it is living there in a cloud, and usually some sensor data is fed into it. So basically you can use that replica or twin then to start investigating what is your physical replica actually doing. If you get some sensor data from your physical product, and if there is something alarming there, you can go and use your digital twin simulation system to check out if it will cause some trouble, if there will be too much of fatigue somewhere that might cause breaking up of some part or so on. And then basically it enables that you can design the system as a full operational unit. So you just don't check those separate things, but you actually investigate them all together. So basically that is system that allows you to monitor the operation of the physical unit, and also it is a sort of entity that allows you to optimize the full system in general from the very beginning. And well, obvious benefits here as well are the improved R&D, because you get some feedback about your design and its operation. For example, if it's there somewhere on the site, and then there is sensors connected to it, and then you can sort of investigate and monitor what your physical asset is doing there on the site, using this digital twin with sensor data connected. So basically, you kind of you have your, if you have doing some simulations already, you know that there are some boundary conditions you need to have first in order to start the simulation. So you can consider this sensor data as that boundary condition, that you have first built your system, digital twin, and then you feed the data into it, and then you can use this data as sort of initial condition to start investigating how it's living there, how a windmill is doing on the seashore, for example. And then obviously you get some feedback also for your future systems. And then one important thing that our customer is very keen on is this predictive maintenance, that they can monitor their system with this digital twin and with the sensors connected into it. So it helps them to design and when it should be good to have a maintenance break and so forth. And obviously it's cost efficient. You can have a digital replica of all of your assets, and for example you don't need to send someone all the time on the site to investigate what's, for example, a windmill farm doing at sea, for example. So it saves time and resources. Yeah. And well, one obvious benefit is that you can then have digital twin for each physical asset. And then what also is very significant is that you can follow up the cumulative effects when you continuously feed the sensor data. So you use it, for example, if the base of the windmill is if it will be wearing out, and when it will be wearing out. So if you may need to change some parts there. So just going briefly through how one actually can build this type of digital twin. So first you have your detailed high fidelity model, for example, for your CFD or structural analysis or electromagnetics or thermal or semiconductor or whatever you might have there, whatever the phenomena taking place in your product. So you have your detailed model for that, but those, maybe you know that they are very heavy. It takes quite a lot of time to run such a case, so they are not practical to be used for this type of real-time or online monitoring. So one needs to build up this reduced order model. Is this concept familiar to you? Yeah. So you use your heavy models, so to speak, to come up with this ROM to make it lighter and faster. And then you usually need to have some control logic system there as well to be able to control, for example, if in a windmill, if there is some limit for pitch angle, for example. So if it's exceeded, then something happens and so forth. And then use this system simulation to actually compile this all. And then finally you have it compiled in one place. Then you need to have this IoT platform if you want to collect the sensor data and have it running there on the cloud online all the time. So then this IoT connection or platform is needed. So as we all go more or less digital. So do the products, and so does the laboratory. So basically, this is just one single picture of showing the thing I have been trying to talk for now nearly an hour. So first you have your digital concept. You do some rough sketching to build up your 3D thing. Then you do some digital prototyping for it, do some simulations to check if the bits and parts are operating well together and if the system is working well. And then you can also utilize some digital manufacturing if some parts needs to be printed in 3D. So for that as well, there is a digital lab, so you can actually simulate the printing process and check out if the part will be forming as it should, or is there some remaining stresses or some deformation in the print. So you can do that as well. And finally, you have your digital twin if you want to put it somewhere in the cloud. So what it means with this sort of ANSYS language that we are using. So just kind of repeating things, but just showing it in a bit different way, so maybe it will become more clear. So first, you have all these different parts that you may have been investigating. And then you have this system simulation, it's called ANSYS Twin Builder, where you can actually put all of things together. And there is, I think, in this Twin Builder, there is own ROM generator, but usually in each of these separate tools there is its own ROM generator, so you can basically just compile and bring all the ROMs into this system simulation tool. And there you have system libraries that might be needed. There is some functional mock-up units for other simulation workflows, and then you have all of those validated 3D models there. So basically you have one single platform where you can put all this stuff in and make a digital twin out of it and put it in a cloud, and it can hang around there happily ever after. Well, obviously you need to maybe validate it from time to time to check if the models are good, or if something needs to be modified a bit and so forth. But basically, within this ANSYS technology, what we are using for our customers, you have all the tools to do these things. And then a few words about this lifetime prediction in general. So basically, you can already do it in an early design phase. For example, you can do, and you usually do this, some fatigue calculation or check if there is some erosion or mechanical wear or something that is happening outside your design envelope. So these are kind of the things that you may know in advance. You may know where your product is going to be operating. So you can consider these things as a starters for your design. And making a bit of difference, what can be called as traditional way and the predictive way, that is this, in this traditional way there is an assumption of loads, for example, that the product will be experiencing. So you design this product based on these assumptions you have, but this most often is not the case. It's not the actual loading that the design is experiencing. And then obviously it's not so easy then to for anticipated or before you have assumed. But this predictive way is based on these live calculations, which is then based on this measured data on the site. So as I explained with this digital twin, you can feed your sensor data into it and do the real-time simulations, and then you immediately see if there has been some, well, let's say earthquake, and your product is suffered a lot of damage due to that, and then you immediately know that, well, this bolt is going to break, it needs to be fixed. And on the other hand, if you have sensor data showing that everything is going smoothly, and if on the traditional way you would do the maintenance this week, maybe you can then postpone it into a month or so. And obviously, when you have this real-time observation of your thing, you can use it to improve the design even further for the next generation of products. So this is briefly just to show it in a timeline, kind of what it means. So you have your physical unit, and then you have your digital twin. You have sensors in your physical unit, and then you can use this sensor data, not only this type of traffic light thing that, oh damn, now there was an explosion. Well, obviously nothing can be done if there is an explosion, but yeah, that was not so good example, but still, maybe you get the point of what I was trying to say. So once you have this digital twin living its parallel life to the physical asset, you can monitor it nicely in the cloud environment, and then you can more reliably predict how it will be living, if it will be aging in 5 years or 10 years, or if it has aged already. Yeah, and then one example of kind of process parameters of digital twin of a windmill here. So basically, if we consider a windmill, you obviously have the wind angle and velocity, and then pitch angle of the blades. That then you can, well, you can really alter the wind conditions, but you can alter the pitch angle. So basically, if you check this lower branch, you can check the mechanical loads based on the vibrations the tower is experiencing, and then you can see if there is some weld fatigue or damage going on if you keep monitoring it all the time. And then on the other hand, you can observe this desired current that it's producing, if it's like if the power and voltage and current are in the desired range, or if it has to be monitored. And then if it's exceeding its limit, then you can go and change the pitch angle, and depending on the wind conditions, for example, to see that the voltage and current produced are as they are supposed to be. So basically the quality part of the thing. So any questions at this stage? So I'm just going to show again a couple of videos of something that is currently being kind of a hype or mega trend. So, well, first obviously is this autonomous vehicles. Let's see if there is. Yes.
The autonomous revolution is all about safety. It's engineering vehicles that can flawlessly adapt to arbitrary and changing road conditions. It's about teaching cars to expect the unexpected. And there's only one way to do this: simulation. Only one company is building the industry's first integrated platform for simulating autonomous vehicles: ANSYS. In order to accurately simulate, control, and test autonomous driving scenarios, many different components must come together in a cohesive and reliable framework. The following demonstration showcases the ANSYS solution. The system that we consider in this demo should realize autonomous driving in different modes, including a full autonomous driving mode and an adaptive cruise control mode. To realize these different modes, we have two planning components and a selector that selects the appropriate plan, either based on adaptive cruise control or fully autonomously based on perception. With the help of Medini Analyze, we can systematically identify the potential hazards that could be caused by malfunctioning behavior of our system components and evaluate their risks. By applying safety analysis techniques like fault trees in Medini, we can derive functional safety requirements. Obviously, it must be ensured that the car avoids collisions with pedestrians. This is a safety goal of the highest safety integrity level, ASIL D. These functional safety requirements must be allocated to our system components. Can AI and machine learning do the job in guaranteeing safety? We cannot allocate safety requirements based on this architecture, and we cannot verify these safety requirements or trace the neural network up to high-level system requirements. That means we must change our architecture and introduce additional components to ensure safety. This is where the safety gate concept is important. It's used to check if the outputs from the AI planner violate any of the safety rules developed for this system, and it gets the safety requirements allocated to it. A safing plan is introduced, as we must do something even if we cannot use the primary and secondary plan. In order to develop the embedded software that will implement the safety gates and adaptive cruise control functions of our system according to the allocated safety requirements with ASIL D, we will build these controls and generate the code with SCADE Suite, which is qualified for ISO 26262 code generation up to ASIL D. The adaptive cruise control mode ensures that the autonomous vehicle follows a safe distance and at a safe speed behind other vehicles on the road. The safety gates and selector determines what happens if an obstacle is encountered in the planned path. At this point, we can now simulate our system in a virtual environment. With Ansys VR Experience, we can create the virtual world scenario with all the necessary traffic elements. Here we have the Ego vehicle, highlighted in green and controlled by the SCADE logic. We start in the adaptive cruise control mode, following the car in front of us at a safe speed and distance. The car in front of us will turn to the right, and we will encounter a pedestrian crossing the road in our path of travel. With Ansys Spios and VRX, we can instantiate and simulate our physics-based sensors interacting with the virtual world, using measured optical properties and operating in different environmental conditions. In this view, we're looking through the Ego driver's view, and we can visualize the LiDAR field of view, update the perspective view, and change the time of day, location, and road conditions. Here's the actual dashboard of our autonomous vehicle. We can see what the driver would see while traveling in the vehicle. This visual dashboard is created with Ansys SCADE display, and the logic behind it is the control code that we discussed earlier, created with SCADE Suite. We can see that the autonomous vehicle starts in cruise control mode, and is following the vehicle ahead of it at a set target speed and following distance. On the bottom of the screen, we can see 2D visualizations in terms of a point cloud and a top-down view of the same 3D LiDAR perception and ground truth data used by SCADE Suite. Even though the AI is telling us to drive straight ahead, the safety gate detects that there's an object in the planned path and invalidates the plan. The selector chooses the next valid plan, which is the safing plan, causing the vehicle to brake at 100% to avoid a collision. We can see the pedestrian walking in front of the car on the depth and perception displays. The pedestrian clears the path of the vehicle, and the Ego vehicle returns to the AI planner mode.
So there was a bit of this embedded software and functional safety things that you need to consider, and also these kind of driving environments that, well, it's not possible to drive 5 times around the globe to test different conditions, but instead you can use these type of simulation platforms to do this test driving and test your control logic and your rules in your autonomous system. Oh, sorry. So I think I will skip this one and and just because I think I'm exceeding my time. I promised to give 60 minutes, but I think I'm going in 70 already. So I'm gonna just show this one video about 5G things that is quite hip also now.
If you were asked to engineer the future, you would start with connectivity. 5G connectivity, to be exact, launching a new era in internet-enabled intelligence, an era that would leave no product or industry untouched. You would fundamentally rethink the way products are developed. You would deploy and depend on ANSYS, a holistic simulation platform that can help you address the staggering requirements of 5G. One that can overcome the enormous complexity, safety, and performance needs of this connected world. That can simulate wireless systems and the infrastructure they operate on. All this with unmatched accuracy, fidelity, and reliability. A proven solution that accounts for mobility and changing environmental conditions. That flawlessly integrates across multiple physics. To engineer this future, you would turn to the only company offering engineers a completely comprehensive simulation solution. Simulation that is pervasive across the product lifecycle, from early design exploration to digital twins providing valuable, real-time operational insights. If you were asked to engineer the future, you would start with 5G connectivity. Where would it end? With a promise to change the world.
So it's quite cool to see actually that nowadays there are so many tools to tackle these problems we have or the new technologies we are developing. So I think it's very exciting times to see what's going on and also maybe to be able to tackle the challenges we are facing. But just to come a bit back to the fast requirements of speed and very fast prototyping and that kind of things. I'm just going to show you one more video and then I think I'm done. So this is something ANSYS has developed a few years back. It's called the Discovery Live, and it's doing everything instantly. So you don't need to actually send your thing to some solver and wait that it's being solved, but you can do your initial prototyping very, very fastly. Oops, it's not...
Disruptively simple, simply revolutionary. The world of product design has just been redesigned. Introducing ANSYS Discovery, simulation technology specifically built for the design engineer. Uniquely built to develop concepts fit for their purpose. Early design concepts that come with directional guidance, validation, and proof of performance. Highly interactive in nature, the Discovery environment supports full 3D editing. Discovery works with all common physics types and simulation applications. Quickly make multiple changes and instantly know the performance impact. Instantly validate your concepts without waiting for geometry modifications, meshing, or solving. Choose higher fidelity, high accuracy studies to carefully refine the best of your ideas. Designers can now iterate, refine, and interactively explore the impacts of hundreds of design options in a fraction of the time previously required, saving time in the development process and resulting in better products. Make a geometry change, Discovery instantly begins recomputing the results without starting over. Refine an idea, validate it more thoroughly, more confidently. Perhaps best of all, the Discovery family of products is simple to learn and easy to use, bringing new and exciting insights to every designer. As quickly as designers can generate questions, Discovery tools can provide the answers. This is the promise of rapid.
So if you're sometimes bored with your theory, then you can download this Discovery Live and play around and check how the upward or downward pointing triangles might affect your design. So then just for your own entertainment, student versions of these different tools if you want to try them out. So to make your studies maybe more colorful than just writing equations on the paper. And one where you can actually get full free licenses for this project. So if you are a member or you have this type of student team at your campus, so please contact me so I can help you get some licenses. So here is my email address. You can follow us on Facebook and LinkedIn if you want to see what's happening at our company. There are two groups. There is the company group, this EDA-Medeso simulation, and there is also this EDA-Medeso academics where I try to post, for example, diploma thesis positions and that kind of thing. So if you want to see our open job opportunities and so forth, so check out. So, do you have any questions now?
What is the working language in your company? Is it English or Finnish?
In Finland, we mainly work in Finnish, but in Norway we have various nationalities as well, so they are not only speaking Norwegian. I was there also a couple of years and I came back to Finland last fall, so in our Norwegian office there are other than Norwegian speaking people, but currently in our other offices there are only native Finnish or Danish or Swedish speaking people. Well, obviously in the UK then there is this English, but so far in Finland we are being stuck in being stubborn Finnish speaking. You can learn Finnish always.
Sorry?
You can learn Finnish.
Yeah, it's not that easy.
I know. I'm a
it's
native
to
Finn.
learn consistent Finnish.
Yes, definitely. But then if you learn ANSYS, then you have various opportunities for your career. So it's the technology leader globally, and it's having like 5 times bigger revenue than the other competitors. So that's quite safe bet if you learn ANSYS, so you can use it in your career anyway. Anything else? So you all want to now have your career within simulations? Yes, at least one. So I didn't talk for nearly hour and a half for nothing. I convinced one person. Very good. So, but if you don't have any other questions, I'll let you know and go see your exams. That's exciting, I think. Thank you. Thank you very much.
Kokeillaan, että niitä oli vähän
Voi kauheasti.